Yeah, so hi guys, my name is Orla and I'm currently a final year PhD student at the University of Portsmouth. And today I'm going to talk to you how we can spin truth out of worms and how that's going to help us investigate the impacts of decay and transport and how that will have implications for the palaeocommunity fidelity of the Burgess Shale. Nice long title for you all. So I hope all of you enjoyed the icebreaker last night and that the alcohol is somewhat out of your system now, as we are going to be talking about lots of dead and rotting worms. So I don't mind if you need to leave now if this is a bit too much for you in the morning. So we all are aware of a classic case of expectation versus reality. What we'd like to see in the fossil record is something like this. And it can be compared to maybe making something like a Chewbacca cake. What we'd like to see is a Chewbacca with maybe like a nice soft filling of cream and jam. But what we actually get is normally something like this. Something that we don't really understand. Is it a gremlin? Is it a Chewbacca? Who knows? So what we normally get in the fossil record, unfortunately, is something like this. But then we do have the exception, which is our expectation, and that is the Burgess Shale Lagerstätte and many other Lagerstätte that we find throughout the fossil record. And what this gives us is a better view of a community at its best. So the Burgess Shale is situated in Canada between the provinces of Alberta and British Columbia, and it's really important due to its exceptional fossil preservation. It's also crucial for insights into a critical point of life on Earth, as it's located at 505 million years old in the Cambrian. It's during the Cambrian explosion we get this insight into the origin of all early animal groups on Earth. So it's giving us a really good glimpse into this time. So in more recent years, places like the Burgess Shale has been used to reconstruct a community structure through time. However, there is a problem when we use places like the Burgess Shale to recreate a Cambrian community, as there's still a debate as regards to how much transport this community has undergone. So the fossils, because of their exceptional preservation and the degree of their articulation, it's been argued that they've only been able to survive limited transport or none at all. Whereas the deposits have been suggested as distal turbidity currents. However, in more recent years, they've been redescribed as these mud-rich slurry flows. And this type of flow is going to have really important implications for the durability of soft-bodied organisms and how they could be transported into one community together. So I want to look at a few key issues to try and help solve this problem. First of all, what are the conditions at the time of deposition? Are they distal turbidities? Are they mud-rich slurry flows? We need to go out into the field and we need to find out. Secondly is, can dead and decaying soft-bodied organisms even survive transport if they are flow deposits? And then thirdly, how does this all affect the palaeoecology of the Burgess Shale? So first of all, we went out into the field back in 2015 and we collected some samples to analyse the grain size analysis. We wanted to look at the nature of individual deposits and see what they say, as well as what is the evidence at the Walcroft quarry for sediment density flows. So when we go back to our expectation versus reality, when the ROM expedition goes out here, this is what I was expecting. You get a helicopter, you get generator, electric fence, toilets, even an espresso machine with John Bernard. This was my reality. Nothing. It was just hours of walking. Not that I'm complaining, it was an amazing sight to go, but just lower your expectation, guys, when you do your fieldwork. Slightly disappointed about the helicopter ride, but anyway. So we're here at the Walcroft quarry of the Burgess Shale Formation, and we decided to focus our efforts around the deposits of the greater phyllopod bed, which is this one here. And the reason for this is that this has been logged in considerable detail in the past sedimentologically. So we then focused our efforts and we found certain deposits here of individual ones that showed us evidence of sedimentary processes that could inform us about how to make analog flows for our experimental design. So we logged these at outcrop and then we logged them in thin section. These ones here are the logs from our thin sections. And what we find at outcrop is these important structures that are giving us evidence of sediment density flows. So we have individual deposits that majority contain this clay and silt with these occasional floating quartz grains. We have parallel laminations, we have these shelly debris layers, and really importantly, we find these erosive scoured bases along a lot of the outcrop, and we can see these again time and time in the thin sections as well. And this kind of structures are indicative of tractional transport. So what we have so far is evidence of these a transitional cohesive flow. But what kind of cohesive flow are we looking at? That's the next question that we need to try and start designing an experimental flow. So what we find is when we look at our deposit type, we can relate it to a flow type. And it's something between a quasi-laminar to upper transitional plug flow. So we're using our field work, a little brain work, and we're going to come up with an experimental flow. So what it looks like is you have a laminar flow here, so the majority of the plug, it is laminar, and then as it transcends towards the base, we get a more turbulent base. So in simple terms, laminar looks like this, and towards the bottom, the turbulence looks like this. Yes, I can make this joke because I am Irish. So we're going to feed this into our experimental design. So we have a 2-factorial experimental design in which we have flow duration and pre-transport decay as our variables at 3 parameters, freshly killed, 24 hours and 48 hours decay, as well as these flow durations here, 900 minutes equating to about 15 hours of transport at about 22 kilometers. And then from incorporating our sedimentary processes we saw at the Burgess Shale, we have an 11% concentration of clay at traveling at 0.4 meters per second. So what we're doing is these flows that we're generating are able to generate all the structures that we see at the Burgess Shale. And then we did 5 replicates of each of these experiments. So we use our annular flume tank, we use our polychaete, a soft-bodied organism at its different stages of decay up to 48 hours, and we use our response variable here of the increasing states of degradation. So this is what the polychaete looks like after it's undergone different levels of transport combined with decay. So you have state 1 where it's complete and comes all the way down to state 4 where you get just the chaetae and the jaws remaining at the end, which are very difficult to find in a flume tank. So I don't know if this is going to actually play. This is what the flow looks like when you use it in a, I don't know why it's not going to. Oh yes, sorry. So this is, oh no. This is our flow. I don't know why it does that every time. Anyway, if you don't just lean your heads this way, that's the flow. It's quite slow, not as fun as everyone expecting it to look like. And what our results is at 25 minutes, we get our polychaete at these different times of pre-transport decay. This is what it looks like after transport. At 225 minutes, which is the equivalent to 11 kilometers of transport, after 48 hours decay, we're getting just kind of like a worm structure and some jaws left over. And then interesting, at 900 minutes, that's 15 hours of transport, you're still getting a polychaete. We're still getting a relatively intact soft-bodied organism after these types of flows. So quantitatively, we ran a ordinal logistic regression, and we found that pre-transport decay has a significantly statistical result on the states of degradation to our polychaete. And then when we run post hoc Wallace tests, we find that for each experimental combination of both your transported groups and the control, which is the polychaetes that weren't transported, but at the same, were stagnant for the same amount of flow duration, pre-transport decay was significant at every interval. However, transport duration, really interestingly and really surprisingly to myself, had no statistically significant effect. Therefore, so transport is not causing any further damage to our soft-bodied organism. Its decay is the most important factor here. So when we go and compare our results to the Burgess Shale polychaetes, we compare them to the Burgess Chaeta and Canadia from the ROM, and we find that majority of the specimens, as you would expect, are pristine and intact, and at state 1 of our degradation here, which means that at the Burgess Shale site, decay was probably only allowed to persist for a very short, brief amount of time before these animals were entombed. So to summarize all of this together, this is my reconstruction of the flow, where we first felt, that should say quasi-laminar, there, not quai, to upper transitional plug flow. We know from our evidence from our sedimentology, we have a turbulent suspension cloud above our plug flow here. We have a majority laminar plug that extends towards the base. And then we have the turbulence that's causing these erosive scoured bases. And then within that, we're incorporating organisms that are being picked up, that could be picked up along the flow pipe tens of kilometers away. The Burgess Shale has the potential to be transported quite a significant distance from the experiments that I've shown to you here. And that's going to have really important implications. So to conclude, with this Burgess Shale, from our evidence, is a quasi-laminar to upper transitional plug flow, and that's the conditions at the time of deposition. We can say that dead and decaying worms, they can survive transport relatively intact, even after undergoing some pre-transport decay. And then this is going to affect the palaeoecology of our Burgess Shale. So when we construct community structure, we're assuming that the Burgess Shale is an in-life palaeocommunity. But what I've hoped to show you here is that it really does have the potential to be a conflation of a few communities mixed together. And that we need to think about that when we start to reconstruct the community of the Burgess Shale. So I just want to say thank you especially to ProgPal, who gave me a travel grant to be here today, and to my 4 main supervisors here. Thank you very much.